Okay, so, right, the class is called Stellar Spectroscopy. Basically, it is going to be a lot about spectroscopy and what generates the spectrum. And the point of that is when you observe light, let's face it, as astronomers, that's all we do, okay? We collect light. So we have to know everything about what generated that light, what the light went through. We're all about trying to understand the physics behind where that light came from. That's really what we're after. And so this class is meant to give you some tools to do that. We'll learn what generates an absorption line or an emission line, so we'll have to learn a little bit about atoms. We'll learn a little bit about how the spectra are collected, what the instrument does to the spectrum, so that we can back it out to understand that light better. But the stellar part is going to be the fact that we're going to kind of use stars as our laboratory. There's a lot of places that light gets generated in the universe, and you know, it can be diffuse gas in the intergalactic medium, it can be an H2 region surrounding stars that have just formed, or it can be in a stellar atmosphere. So each one of those is a different physical regime: low density, high temperature, or moderate temperature, high density, and the physics that dominate what type of spectrum you're going to get can be very different. By focusing on stellar, we are going to be limiting ourselves to the type of physics that we have to consider. I would love to someday teach a low-density intergalactic medium type class as well, and then I could talk about the gas physics in those environments. But so we're going to be talking mostly about gas that has very high density, 10 to the 10 to 10 to the 15 grams per cubic centimeter, or I should say atoms per. That's actually number densities. For example, our Earth's atmosphere is around 10 to the 19. So it's fairly dense gas in terms of the gas in the universe. The temperature varies with depth, the chemical composition can, the ionization stages of all the atoms can. So really what you're after when you collect light is you want to try and understand the physics of the gas, the state variables. What's the density? How does the density change along the line of sight? What is the temperature? How does the temperature change along the line of sight? What's the chemical composition? How does the chemical composition change along the line of sight? What's the velocity field? Okay, once you get the velocity field, maybe you can learn something about the energetics of what might be moving the gas in bulk motion, so you learn some more physics there. And it goes on and on and on. So that's what light is. Light is just the surface material that we collect, and then we have to go back to the physics. So in a sense, the class is kind of 50% stellar atmospheres. Okay, and most graduate programs teach a dedicated class to stellar atmospheres. When I was at Santa Cruz, we had a 10-week course, stellar atmospheres. All we did was learn the atmosphere component of what we teach in this class. But I would like to also talk to you more about the atomic physics that goes into generating the spectrum and helping you understand how you model a spectrum to get out that information. Okay. To that effect, what I want to do is have basically a I shouldn't say non-intensive, but a short weekly homework, not long weekly homeworks. Now, short meaning doesn't mean that the time you spend. I'm going to not try and weigh you down, but a lot of the homework is going to involve calculations that are best done by writing a small computer program. And in fact, one of the things that will be the biggest challenge in the course will be that I'll have you do a stellar atmosphere model. I give you a complete handout on the recipe, what physics to put in there, some ideas on how you program it up as an algorithm. But effectively, the idea is for you to write a comprehensive program which will tell you the density, the temperature, and the pressure and the optical depth as a function of height in the atmosphere of a star like the sun. The homework assignments throughout the semester will be basically designed to prepare you for that. In other words, you'll have to calculate the ionization balance at each layer in the star. So one of the homeworks will be calculate the ionization balance in a gas with a certain density, a certain temperature, and then you've got that algorithm. So you'll be building the pieces of code that eventually you can learn to tie together. And that's actually one of the bigger challenges, is tying the pieces together. Yeah?
Is there a specific programming language that you require, or is it?
No. I don't want to tie anybody's hands behind their back, okay? I want you to pay attention to the algorithm and the physics, not learning syntax of a new language, okay? However, I will tell you, I am better at some languages than I am at others. So if you want to come in and get some help, I'm going to really date myself. I speak Fortran backwards, forwards, and upside down. I can do Fortran like nobody's business. C, I got to think about it, and I'm not good with probably the more data structure or subroutine connecting things. I can read the syntax on a couple loops or something and understand the calculation, but the overall broad linkage of subroutines and things like that, I'm not that good at. Some people have been doing it in MATLAB. I've been able to help them with that, and some people have been doing it in Python and things like that. I'm an old schooler. I do everything in Fortran and a little bit of C, because I feel like those are like really robust for scientific calculations with high precision. Then I dump things to files and use a plotting package. So I'm still old school in that regard, not the Python programmer who does the calculation, never looks at the numbers, and out comes the plot. And sometimes you can tell it's right by looking at the plot. So sometimes I think it's smart to look at the numbers too, especially intermediate numbers. If your plot's not coming out right, sometimes it's the intermediate numbers that give you the clues. Okay, so from that standpoint, I'm just going to have a midterm and I'm going to have a final. Sometimes I do them orally, sometimes I do them written. We can discuss that. And then I'm going to have these class notes that you like, the ones you printed out. I'll have those available. They're all online already. I think if you went to the Canvas page and browsed around, you probably saw that they're all there. I also have some things that are teched up in sort of textbook form that I'm going to cut and paste. I'm going to get some of those available as supplementary material too, and in some cases those might be clearer for you to read. So in the end, it's the two midterms, a pretty much weekly homework, probably one problem or two small problems at the most, and then the semester project. And I think I got it out 40% on the homework, 20% on each of the tests, and 20% on the project. So trying to distribute it around so that no one thing really is like, oh my gosh. Obviously, I think doing the homework is really key. I also think reading is key. I don't really want to get on a soapbox, but, and I know everybody's, especially in your first year, you're making a transition with the TAing and the extra duties that go on, but there's no substitute for reading and rereading and reading many different sources. And it gets harder, especially these first 2 years in grad school. And then when you get out of school, out of classes, you start working your research, then you really find that you can read things that really interest you and aren't things that are just needed for passing the classes. However, as a spectroscopist, I feel like what I've tried to do is distill all the tools out, and I want to talk about all the things that, gosh, I wish somebody had taught me that in graduate school. I wish they had taught it the way that I'm going to adopt as a philosophy, because I would feel that that stuff would have been useful to know for my research, and would have, you know, really helped me jumpstart that. So if any of you are ever going to do optical, ultraviolet, or infrared spectroscopy, my hope is this class will be a really good jumping spot for you. That's what's at. And if you're going to study stars, all the much better too. But I don't think that's happening. So a little bit on the sun, but it's usually a lot different than studying, you know, other stars where you're just dealing with regular signal to noises and not these infinite signal to noises. Okay. Okay, so collaboration on the homework is fine, but in the end, when you're done talking to your friend or working something out on a whiteboard, you know, go into your own private space to write it up. Okay. Okay. So any questions about that kind of thing? My goal is going to be, you know, the homework comes out and you give it back to me, and within a week at maximum, I hand it back to you. I wasn't very good last year with that, and it's one of the things that I want to make sure is a strength of this semester. Okay. And I'll ask again, that I keep interrupting the possibility of anybody asking me a question. Are there any questions? Okay. All right, the rest of it is, you know, your standard stuff. Now, I have drawn this material from a lot of different books, so on page 2 here you'll see recommended reading, if you get a chance to read. Okay, or if you're thinking, I'd like to just build a library of material, I have gone through all of these books, the Fundamentals of Stellar Astrophysics, Interpreting Astronomical Spectra, Stellar Atmosphere, Introduction to Stellar Atmospheres, the Solar Atmosphere, and I've earmarked all these books for the different topics we're going to talk about. So if you at any point in time would like to read one of these books or a couple pages out of these books, I've got it. I've got the library. Just come, ask me. Let's have to sign it out for a couple hours. You can check it out. Now, having said that, in the last 3 times I've taught the course, I've yet to have one student come in and ask, look at a book. Okay. All right. So if you looked at the web page, there was basically this introductory notes. Okay, and that basically what I want to do with the introductory notes is just sort of do the general surface overview of what physics is hiding in a spectrum. Okay, that's really what it's all about. Okay, and to teach you about something called optical depth. Okay, and how that relates to the density of the gas and whatnot. So we're going to talk about that in the anatomy of a stellar spectrum itself. And then what we're going to do is we're going to move on to the atoms and their transitions. Then we're going to talk about gas physics. And then we're going to, in the gas physics, we're going to discuss the stellar atmosphere in particular. And one of the things that we'll have to talk about is something called radiative transfer. You cannot be an astronomer and not know radiative transfer. Okay. Now, you don't have to know it as well as Chandrasekhar did. Has anybody looked at Chandrasekhar's book on radiative transfer? Yeah, it'll make you want to just quit and go home. I feel like a complete retard when I look in that book. It's so above my head. But it turns out you can succeed and not be as knowledgeable as Chandrasekhar. So when you learn radiative transfer, you may learn it more than once in your courses here. And each time you learn it, it will be from person's perspective. And it's really painful. There'll be different notation. You're working in a different gas physics regime, so certain terms won't be talked about, okay, and things like that. So you have to, it's good to see it many ways and from different perspectives, because there's no one way to learn radiative transfer. You have to sort of think about what is it like in stars and learn that. Then what is it like in a diffuse gas cloud and then learn about that. And it's sort of one time at a thing way to learn it. So You're going to see it here mostly in the perspective of the stellar atmosphere. I believe Renee is still teaching the interstellar medium, and he will teach radiative transfer, and it will be slightly different with slightly different terms, but the principles are the same. Even John, I think, takes a stab at it.
Every class.
Okay.
Every takes
Says-
classes.
Okay, why? Because you can't be an astronomer and not know how light interacts with matter. I'm sorry. If you don't want to know that, you're in the wrong field. Okay. All right. So, yeah. And then one of the things that I like to get to is the detailed thing of how the light actually talks to the atoms. Okay, so we'll learn about the structure of the atom a little bit and learn about things like fine structure. Anybody heard of fine structure? Maybe you've heard the fine structure constant. You know, when you've studied the atom, you've probably, of course, seen the Bohr atom many, many times. Has anybody taught you the physics of the Dirac atom, for example? Okay, well, in a lot of spectra, you see multiplets and doublets of lines coming from transition. Okay, if you studied the Bohr and the Schrodinger atom, it does not handle multiplets and triplets and doublets and things like that. You have to sort of go into the next level with the model that Dirac put together. So I like to teach that because I feel like that doesn't really get talked about. And when you go and see a talk and someone says, well, the carbon 4 doublet or the oxygen 6 doublet or the magnesium 2 doublet, it's like, okay, well, it comes as a doublet, but why? You know, what's the physics there? And, you know, if you're going to do spectroscopy, you probably, that's pretty basic, actually, in the grand scheme of things. We're also going to talk about something called the curve of growth, which is something that I like to talk about. You might see that in Renee's class as well. I don't know, but if somebody could shake their head. Okay. And then I'll talk about something called continuum opacities. Okay. You know, you've seen spectra of stars, maybe in the introductory textbooks. And, you know, the O star has this nice, beautiful black body. The A star goes like this, and then has this drop off. You know, and the M stars, they're all crazy like this. You know, so why is that? Why are those spectra so different? Because it's not just about atomic bound transitions that creates the overall shape of the spectrum. That's what we call the continuum opacity. So we need to talk about the continuum opacity. That will teach us why the different stars have very different shapes overall to their spectra, and also for galaxies. Why? What are galaxies made of? Lots of stars, right? So, okay. So that's about it. And then if there's time at the end, I like to go through the zoology of spectra, the nitty-gritty of the classifications. But I often run out of time for that. But the notes are there, and chances are that nobody is going to get into the business of becoming a professional spectroscopic classification astronomer. So if you need to know that, there one of these books, the one by oh, imagine that, I dropped it from the list.
Gray and Corbally.
Gray and Corbally, right? Everything you want to know about every line and every spectral classification that exists, at least to the level that is known as of a few years ago. Okay, so having said that, let me talk to you now a little bit about what makes the spectrum, and from the very general point of view. Now, there's a little write-up here, which is a summary of the things I'm about to say right now. And this is by a fellow by the name of Mike Briley, who is very, very well known in the stellar spectroscopy community. And I basically put a little bit of outlines around the different parts. And you can basically break up what makes a stellar spectrum due to a very set of simple variables. Okay, and basically, it's too simple to write down. On page 1 here you can see you've got the metallicity and the abundances. okay? So if you can have some absorption lines, if you have greater metallicity, for example, it's possible that the absorption lines will be deeper because you have more atoms along that line of sight for that metal, okay? So the number of absorbing atoms or a number of emitters. And what we're going to do is we're going to find out later that that's related to something that is measurable called the column density. So maybe you've heard of the term column density. We're going to talk about that a little bit later today. And one of the things that's going to be very important to understand is something called the electron density, because the gas will be partially ionized, which is to say that some of the atoms have electrons stripped from them. And given the temperature and the density, the number of electrons stripped will normally go up with temperature and normally go up as density decreases. Okay, usually, well, in a low density regime, the number of electrons being freed, or the ionization level, will usually go up as the density goes down. Because in a low density regime, it's actually the photons in the gas that are causing the ionizations. In a high density regime, this will all become clearer later, but today is the fire hose, drink from the fire hose day, okay? As the gas density goes up, then collisional ionizations will be more important. And so, therefore, the higher the density, the higher the ionization. So, there's a low density regime, ionization goes up with lower density, and high density regime, it goes up with higher density. So you can't always just take a rule of thumb and go with it. You have to know what regime you're in, okay? So the electron density is basically the density of all those stripped off free electrons that are zooming around in the gas, okay? And it turns out that every electron, when it goes past an atom, kind of makes an electromagnetic disturbance. Electromagnetic disturbance to an atom means that its energy levels of the bound electrons get changed a little bit and blurred. And so now when photons come through, they're seeing a slightly different atom than they would if it was unperturbed. So that can affect the shape of a spectral line as well. So there's all kinds of stuff going on. And believe it or not, there's almost, for the most part, these one-to-one correspondences with the shape of a line and what physics is giving rise to it. There are degeneracies, and that's where things get hard. But you can really get trained enough to look at a spectrum and say, hey, that's pressure broadening. That's stark linear broadening of the hydrogen alpha line because of the electron density. You can get to that point. Okay. That's my goal, to have you look at a spectrum at the end of it. No, that's a pretty ambitious goal. Okay. Okay, so I mentioned temperature. Temperature, obviously. First of all, the higher the temperature, the faster atoms are moving around. Okay, and you get something called Doppler broadening of an absorption line. Okay, so an atom at rest that absorbs, say, 1215.6017 for the Lyman alpha line, boom, right on the money. Okay, but if the atom's moving toward the light beam, okay, then it's no longer going to absorb. In its rest frame, it absorbs what it sees are 1215.601s, but in our frame here, it's going to absorb redder or bluer. It's moving away from you. Okay. In its rest frame, it's the redder photons in our frame that have 1215.6017. So atoms moving away from you absorb redder light in your frame, and atoms moving toward you will absorb bluer light in your frame. So you can think about it in your frame, but what's fun to twist your brain is sit on the atom and think of the light beam coming toward you from the atom's frame and see what happens. And if you can do that, you are a long way on the road to being able to interpret spectra and understand gas physics. I like to tell this story briefly. Lyman Spitzer. How many people have heard of Lyman Spitzer? One. Oh my. Two. All right. All right. One of the most famous astronomers from Princeton there ever was. Heard of the Spitzer telescope by chance? Okay. All right. So one day he comes home from work, and his children say to him, "Daddy, what'd you do at work today?" And he thought for a second, he goes, I sat all day in my office and thought about what it's like to be an electron in a gas. So if it works for Lyman Spitzer, it can work for you. That's my point there. Okay. And then the thing about temperature and the Doppler broadening is that one of the simple things that we measure from a spectral line is its strength. Okay, what do I mean by that? Okay, so if you have an absorption line here, okay, let's say this is the continuum light and this is the absorption line. We usually measure its strength by measuring the area in here, and we give a name for that, which we'll talk about more in detail later. It's called the equivalent width. Okay, so this line would be weaker than, say, this line, because the area of the light removed here is a lot larger. Okay, so it turns out that this measurement of the absorption strength, or the equivalent width, also depends upon the gas temperature, right? Reason is because it turns out that if the gas is at higher temperature, the atoms are moving more rapidly, so you get greater Doppler shifts and blue shifting and red shifting, and the line gets broader. So, for example, if it was hotter gas, this line would look more like this, and therefore there's more area taken out of it. And you have to account for that when you're doing these calculations. Does it make sense to everybody on the surface of it? Okay. This behavior with the gas property is we know it's called the curve of growth, and this is a relationship. The curve of growth is a relationship, sometimes known as the cog, and it's a relationship between the column density and the equivalent width. Okay, so capital N is column density. I'll just draw you the curve now, and then we'll explain it later. It goes something like this. Okay. At small columns, very steep and linear. At moderate columns, it's flat, and at large columns, it's actually flatter. It goes up, but it's flatter. Okay. So something like that. And we're going to talk about this in detail because this is very important for analyzing spectrum. Okay, microturbulence is another form of the gas motions. So there's the Doppler effect from the temperature, but then the gas may have small bulk motions, such as convection, rising and sinking. That also is a bulk thing that can shift a line or broaden a line or make an asymmetry in the broadening of the line. Okay, so a lot of things can happen there. All right. The second thing about temperature, I got temperature number 2 here under, gee, you think I can't count, 1, 2, 3, 3. Under the second 3 is temperature 2, and that because when the gas is in, this is a very important point, when the gas is in equilibrium with the photon field, then the shape of the photon field and intensity of the photon field depends on the temperature of the gas. So if the photons and the gas are in equilibrium, thermal equilibrium, we'll talk about that later, then the photon field depends upon the temperature of the gas as well. And a photon field can also be responsible for photoionizing the gas. Okay, and then you get into the electron density and you're back into that whole ionization balance thing. Okay. Now, the other thing is that the density of the gas matters, and the density of the gas can be governed also by its temperature, but also by the mass of the star and the size of the star. Okay, okay, it's what we call the surface gravity. Okay, it turns out, we're going to find out that there's something in absorption lines called pressure broadening. Okay, and pressure broadening can do very funny things to lines. Let's say we have a line that would look like this normally, but in a star where the gas density is very high, it may end up looking something like this. So this would be pressure broadened. So you can have a star with the same temperature, okay, and basically very near same ionization conditions and metallicities and whatnot. But if you are in a much higher pressure or higher density environment, your line can end up looking like this. When does this happen? It turns out that this behavior is proportional to the pressure, P, and it turns out that the pressure itself is proportional to the surface gravity of the star to the 1/3 power-ish. Okay, and what is G? G is basically mass of the star divided by the radius of the star. If I got that right? Okay. So effectively, you can see that the mass and radius of the star play into the surface gravity of the atmosphere where the light is coming from, and that the pressure goes as about the 1/3 power of that, and then we'll talk later about how the pressure broadening causes these lines to change. Okay? I'm only on the first page. Okay. And then stellar rotation. Okay. This again is the Doppler effect. Okay? When you take the spectrum of a star, an unresolved star, you're getting light from its entire surface. Okay? And if the star is not rotating, then you basically are just getting the Doppler shifts broadening from the thermal, maybe some turbulence. Now rotate that whole star, this whole limb is coming towards you. Makes broader blue wing in the absorption lines. This part of the star is moving toward you, makes a broader red line. Okay. So what does that look like? It's a very odd looking shape. Okay. If this is a normal line, if you have a rapidly rotating star, it actually does something like this. That's rotational broadening. So, now, you can imagine that when you take all of these things into consideration, pressure broadening, rotational broadening, Doppler broadening, turbulent broadening, whether it's symmetric or not, you can get a whole host of line shapes in your spectrum. And just for good measure, guess what the instrument does? It blurs them out too. Okay, it's called an instrumental spread function, and it will slightly modify the shape of the line by the time it gets recorded through the camera. Thank you very much, Instrument Builder, but they're doing the best they can. And then it gets collected by a CCD, which breaks it up only into points, for which you have data points, and there's noise. Okay, so in the end, if you're really noisy, can you tell the difference between that and that? God, I hope your spectrograph and your data are better than that. But you see what I'm saying is you do get a little bit of mud on your lens when you're doing your analysis. So, yeah, it's a tricky business. That's why spectroscopists get paid the big bucks. All right. Talk to my wife about that. She doesn't really agree with that too much. I'm only playing around and joking. Okay, so that is sort of my introduction. And I know it's a long class period. We go till 1, right? Mm-hmm. Oh my gosh.
We have nap time now.
I know. I know. Plus it's lunchtime, and I'm like, please eat beforehand. And then it's like, okay, well, that means you're all going to be tired digesting, so probably should eat afterwards, but no, I have to go teach lab then. So, if you're having issues with the eating, let me know. We can work something through. I really was just hoping it wasn't going to be a lunchtime round table. So, but we can talk about that. All right. So let's talk about the anatomy of the line, and then I want to talk to you about some variables that you're going to be seeing all semester long that today you might be a little bit about them, but with time we were going to talk about them in detail. Okay. All right, so this is what the fuss is all about. I've already drawn a couple pictures on the board, this nature. Okay, this is a picture of a typical absorption line with a continuum. The anatomy of an absorption line, okay, it has a core, it has wings, and it has the continuum on both sides of it. Okay, now the reason I'm bringing up those words is because we're going to be saying those words throughout the semester. They have quite specific meaning, and it turns out that what goes on in the core can be very different physics than what goes on in the wings. Okay, so the core can be driven by certain physics, the wings can be driven by other physics, and so that's why we actually have broken that down. It's not just sort of a pretty picture, this is the middle and this is the side kind of thing. Okay, all right. So I talked a little bit about the continuum. We're gonna show that the continuum shape has a heck of a lot to do with, guess what? The number of free electrons in the gas. The number of free electrons turn out to be